Hello, this is Information Service Engineering, lecture number 5, Basic Machine Learning. In this part of the lecture, we are going to see the second part of the basic machine learning algorithms. And more specifically, we will focus into decision trees. So, in many classification problems, as well as in linear regression, we expect all the attribute values to be present at the same time. But actually, sometimes new attributes occur only over the time. And in these cases, it's more efficient first to check the most promising attributes before moving to other attributes. Consider, for example, here the physician and when they examine a patient. So obviously they don't run all the tests at the same time. They have a list of tests, they start from the most promising tests, and then if those fail, they go to the other tests, but not everything at the same time. So this is the idea also behind the decision trees. Let's consider another example. We want to answer the following question. Should we play tennis today? So let's see how these decision trees will help us decide. So in order to make this decision, we are dependent on some facts or attributes here. So the attributes are the outlook, the wind, the temperature, and the humidity. And you see here in this tree, which is created by a given set of possible instances, that we have the internal nodes, or where are the test attributes, the output, the humidity, and the wind. Then we have branches between for those nodes, which those branches they select specific values for the attributes. For example, there is the branch sunny after outlook, or the branch overcast after outlook. And in the end, we have also the leaf nodes, which are the predictions y. And you see that in the leaf nodes, we have either yes or no, which is the prediction for the given question we have here. Should we play tennis or not? But then let's try to make it a bit more formal here and see how is the decision tree learning process. So the problem setting is the following. We have a set of possible instances x, where each instance x is a feature vector of this form. We have also an unknown target function f, where relates the x with the decision y, where y is a discrete valued. And then we have a set of function hypotheses h, where each hypothesis here, h is a decision tree. The input for this algorithm is training examples of the form x, y of an unknown target function f, and the output is the hypothesis h that best approximates the target function f. So in general, a decision tree represents a disjunction of conjunctions of constraints on the attribute values of instances. And it might sound complicated, but is not if you read it again and pay a bit attention. So let's see what this means in the given decision tree we have here. So the given decision tree corresponds to outlook equals to sunny and humidity equals to low, or outlook equals to overcast, or outlook equals to rain and wind equals to weak. Those are the cases that the decision tree we have here gives us the answer yes to the original question or the original attribute we wanted to predict. And because of this, decision trees can represent any function. So, to construct a decision tree is a relatively easy task. Given n features, there are n factorial possible decision trees we can make out of those. But unfortunately here a decision tree can grow very large because again, given n features with m possible choices for those features, you realize that the decision tree can grow up to the size of m in the power of n. Can be pretty huge. The decision trees also here, they depend on the order of the features. And the learning algorithm, in this case, tries to determine a good ordering, which we are going to see how it works later on in this part of the lecture. But what I want to mention here is that learning the simplest or the smallest decision tree is an NP-complete problem. So if you are more interested to learn more about it, you can check the related work that we have here in this slide. So, in this part of the lecture, we are going to focus in ID3 algorithm of resort to greedy heuristic. So the steps of this algorithm are the following. First, we start from an empty decision tree, and then we split on the next best attribute, and we recurse. And the question here is, what is this next best attribute? How can I find it? Well, we are going to use information theory to guide us and help us here for this task. So, let's consider a smaller example. Here we have this data set. We have the features x sub 1, x sub 2, and the y, which in the end we want to be able to model or predict. And the question here is, which attribute is better to split? X sub 1 or x sub 2 here? And the idea which we follow is that we use the counts at the leaf nodes here to define the probability distributions, so that we can measure the levels of uncertainty that they will give us. You see here that in the branch true of x sub 1, if we follow this branch, then we will have 4 cases where the y gets the value true and 0 cases where it gets the value false. But while if we follow, for example, the branch false for x sub 2, we see that the y gets twice the value true and twice again the value false. So let's see how we apply this idea of counts in the leaf nodes of how the features will affect y, and to count this information and make it real so that we can really make a decision about it, we are going to use the information content or entropy. So entropy of a feature variable x with n possible feature values, here in this example we have 2 feature values, true and false, is based on its relative frequency of occurrence, which is nothing more than the probability of this event, and is given by the following formula that you see. It's really simple, this formula. We just have to measure the probability, and the unit to measure the information content here is the bit. So let's see how we apply this formula to compute the entropy of y here. So we see that we have 8 cases. In 5 out of 8, the y has the value true, while in the rest 3 has the value false. So if we apply the formula of the entropy, you see here that first we have to compute the probability, which is 5 divided to 8, and then the logarithm of this probability minus the probability of the false cases, which is 3 divided to 8, and the logarithm of this 3 divided to 8. And finally, we get the result 0.95 bit, which is the entropy of y as it is now. So this is a curve that shows us the relation of the entropy and this probability b, and what I want you to get out of this figure is that the worst case scenario that can happen to us is when the entropy is equal to 1, which is there in the top. This is the uniform distribution of the values, and that means that the sample values are less likely predictable. So they are completely uncertain. So this is the case when we have 50-50 cases. So in 50% of the cases I have true as a result, and the other 50% I have false as a result. So this is completely uncertain. While the best case scenario for the entropy is when the entropy has value equals to 0, and that means that the sampled values are better predictable. For example, when I know that in this case, in this branch, I have 100% of the cases it's true and 0% is false. So these values are better predictable here. But then in the end, still we don't know how we decide on which feature to split. And for that, we are going to use the information gain. So the information gain of a feature y due to a feature x is the measure of effectiveness of a feature in classifying the training data. In other words, it's simply the expected reduction in entropy caused by partitioning the example according to this specific feature. And the idea is here, if we know how to compute the information gain for all these attributes we have, we can do it for all of them and pick the one with the best information gain. So the information gain is given by the following equation, where first we have to compute the entropy of y minus the entropy of y given x, and is transformed to the last equation here, where here x are all the possible values of the feature x capital, in our case, in our example, true and false, and y of x is a subset of all instances in y with that specific value, either true or false. So let's see now, if we apply the information gain formula, can we decide if x1 or x2 is the best attribute on which we are going to split? So first we apply it for x1, and what do we need? We need first the entropy of y, which we computed in the previous step, is 0.95, and then we continue with the rest. So we see here that there are 8 cases. First we do it for the true branch, true value of x sub 1. So we have 4 out of 8 cases represented here, and then we have to compute the entropy of x sub 1 for the true value, plus the same procedure for the false branch. So 4 divided to 8, and then we have to compute the entropy of x1 being false. And that gives us the result that we see here, the final result, where is the information gain of y given x sub 1, meaning splitting based on x sub 1, is 0.55. What I want you to note here is that the information, the entropy that comes from the branch of true in x sub 1 is 0, because it is completely certain here. We know that all the cases are true, so that's why this entropy is 0. And we do the same procedure for the x sub 2. So again, we need the entropy of y, we have it, and then we check first for the branch of the true and then for the branch of false, and finally we end up with 0.05 as information gain if we split based on x sub 2. So which is the best split here? Which attribute should we pick? Well, the answer is x1, of course, because this is the one who gives us the more information gain if we split based on it. So, visiting again the ID3 algorithm, now the steps are, of course, the following. We start from an empty tree, we split on the next best attribute, but now we know how. We know how we decide what is the best next attribute. We use the information gain, it's the one with the highest information gain, and then we recurse. So if we go in the initial example of playing tennis here, this is the full data set, let's say, we have, and we just want to make the play tennis predictions. So what do? We are going to compute the information gain for all these attributes we have here: outlook, temperature, humidity, and wind. And if we do it, compute it, you see here that the one that gives us the best information gain is the one of outlook. So obviously first we are going to split based on outlook. And then we continue to the branches that are not certain. And we leave out those where they give already entropy equals to 0. So for the branch of overcast, now we are not going to split further because it's perfect as it is. It gives us entropy equals to 0. We are going to continue for the other branches. So then, given now outlook, what is the best attribute, which is the next best attribute to split on? So now we are going to check humidity, temperature, and wind and compute the information gain for all of them. If we do it, we see that humidity gives us the highest information gain, so we split based on humidity, and by continuing the same process recursively, we end up in the this decision tree, the one that we saw in our first slides of this lecture. So pretty simple as that. So now to summarize, there are of course advantages and disadvantages for this algorithm as well as for every algorithm. Some of them is that it's simple to understand and interpret, is able to handle both numerical and categorical data, It requires little data preparation. It uses the white box model approach. It's possible to validate a model using statistical tests here. It performs well with large datasets, and it mirrors the human decision making more closely than any other approach and algorithm. But the main disadvantage here, and be careful, is that decision tree models easily overfit, so be careful for that. And here we have the list of the decision tree learning algorithms you can use. First we have the ID3, which is the algorithm we just presented here in this lecture. Then it comes the C4.5, which is the successor of ID3. We have also the CART algorithm, which is the classification and regression tree. The CHAID algorithm, which performs multi-level splits when we compute these classification trees. And last we have the MARS algorithm, which extends the decision tree to handle better numerical data. So, in the next part of the lecture, we are going to talk about unsupervised learning.